So what we have here is the channel 1 is the signal coming from the computer sound card that we send to the same sine wave input of the speaker. That is split, and one goes to channel 1. And in channel 2 we see the signal from the AC monitor coming after the amplification and attenuation of the microphone output. So I'm going to run this controlling the data acquisition with the Spectrum SLC code, and we're going to scan from 100 Hz to 10 kilohertz. Start the scan from a low frequency. Here you can kind of get an idea of the frequency. The scope is trying to measure the frequency here without much success as it's continuously changing. But you see the increase of the amplitude in the output of the microphone when we go through each resonance. And we just ended the scan. So the scale of the scope is set at 1 millisecond per subdivision in the time, and for channel 2, the output of the microphone, the scale is 100 millivolt per subdivision. Now I will repeat the same measurement, but looking at it from the Spectrum SLC code. You see that the start frequency is 100 Hz, the stop frequency at 10 kilohertz. We take steps of 10 Hz and spend 50 milliseconds at each step measuring the output of the microphone. The signals are not split going into the electronics now. This is the only difference, but basically it's the same as the previous video. And we start the scan. Look at the changing scale in the x-axis. This is the first peak, likely due to noise, and this is probably the first true resonance. The second one is a bit above 2 kilohertz. We reach 10 kilohertz, and that's the end of the scan. So we can save this, save the spectrum as some .dat file. Test run .dat. And this is done with a tube of 15 centimeters in length.